Hi everyone and welcome back. On this video, I will try to explain how general relativity makes a better job at explaining experimental evidence that we have, such as black hole, gravitational waves, and all of those compared to Newton's theory. So I will just outline some experimental evidence, yeah, and explain how GR does a better job. Let me share a whiteboard, and as usual, I advise that you adjust the playback speed probably to 1.25. And we can start. So how does general relativity make a better job at explaining the world, kind of? So we have experimental evidence. We have experimental evidence. And probably the first one to talk about is that for a long time, we've known that the orbits of Mercury were precessing, which means that if this is the Sun, Mercury orbits, that's one orbit, and then the second one will precess and precess and precess and precess and precess in this manner. So this we observed it for a long time, but Newton's theory never explained why. And this is one of the first computation Einstein did with his new theory. So precession of Mercury. And in fact, general relativity did a better job, quite a very, 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 very accurate job at computing the orbits of Mercury. And this can be seen by comparing the effective potentials for orbits in Newton. In the last video, we've seen that it was something like this. If we have energy, and no, and radius, energy and radius. So that's the potential, the effective potential in Newton theory, but in we've seen that in Einstein theory something more like this, and the difference is that here it is a perfect well, and then it does like this, but here it's not a perfect well at all, and the ellipses here, they won't close, and because they won't close, it means that for an orbit, this is R minimum and R maximum, so R minimum and R maximum. And it means that the eclipse will never, for example, will always come back to R min, but will never go back to R max. So it means that then R max is here and come back to R min, R max is here, R max is here, R max is here, and R max is here. And so it precesses because it never comes back to the previous R max here, R max, because the ellipse, sorry, won't close. And so we have a orbit precession because not only Mercury precess in orbit, but in general all ellipse precess. So the precession of Mercury is one of the first experimental evidence. Then we have the deflection of light. We know that matter or energy is deflecting light, so the deflection of light by matter, so I will put m/e, so by matter or energy, they're both the same. So we know that light is deflected by this, and actually the first observation in 1919 during a solar eclipse shown that the position of the star behind the sun were uh, deflected. So Newton does not explain why gravity, in Newton, gravity is only an interaction between massive objects, but light has no mass. So Newton does not predict that light should be bent, but actually it's because GR said that mass curve spacetime, and because light is following geodesic, then the trajectory of light is bent by a massive object. And so GR, by explaining the whole thing with space-time curvature, is predicting that light will not escape that because it has to travel in the universe just as any other object. So light will be deflected by a massive object. And so this is one more thing that GR explained that Newton does not even mention. Just as the Mercury precession, Newton does not even does not predict. Yes, so 1919, first observation. Okay, then we have also the expansion of the universe. Today we know that the universe is expanding because of the cosmological redshift, which means that galaxies are moving away from each other at the same rate as universe is expanding. The expansion of the universe, the first observation of observation of cosmological redshift. Redshift is Z, so we'll let Z. Observation of cosmological redshift was made by Hubble in 1929 when he discovered that all galaxies were moving away from each other at some rate. And the rate is Hubble constant. Yes, so the expansion of the universe, it's something that we observe and that Newton theory does not predict, but GR does a very good job at it. One more is time dilation in gravitational field. All right. Time dilation in gravitational field. So this is when you assume both special relativity and the equivalence principle. I did 2 videos about it. If you take special relativity and equivalence principle, then you say that a laboratory on Earth experiencing the gravitational acceleration g, and a laboratory in a spaceship experiencing the acceleration a, because the spaceship is accelerating. Well, if the spaceship has no window and the laboratory has no window, and if you make the acceleration of the spaceship being the same value as the acceleration on Earth when someone fall on the ground with some acceleration, then the equivalence principle say that there is no physical experiments that could show in which situation you are. But we know that in an accelerating spaceship from special relativity, we know that we will have time dilation between a clock on the ground and a clock on the ceiling. And so the same should apply on Earth between a clock on the ground and a clock on the ceiling. And so we have time dilation in gravitational field. And the first time we checked that was in 1971. So First observation, again, I will put first observation, 1971, when they started two atomic clock perfectly indistinguishable. So the two atomic clock were perfectly synchronized, and they were in an airport, and they put one atomic clock in a plane that would go around Earth, and they let one atomic clock at the airport. And when the airplane came back with the atomic clock inside and they compared both atomic clock, there was some time dilation between. There was very, very slight difference in the two atomic clocks that 24 hours before were synchronized and 24 hours after are, are no longer synchronized because the airplane the airplane was at some altitude the whole time while the other clocks stay on the ground. So in Newton theory, time is absolute. In special relativity and general relativity, time is relative. So GR does a better job at explaining why if you take a clock in an airplane, or if you take a clock on the top of the Everest and one clock at the ground of the Everest, after some time, 24 hours, 1 week, 1 month, you will observe the time dilation between those two clocks, and the calculation that you can do with GR are very accurate to what we observe. So time dilation in gravitational field is one more experimental evidence that GR does a better job at explaining the world. All right, then we have also an everyday experiment that everyone does is using the GPS, using Google Maps or whatever ways. Every time you use your GPS, you're using the general relativity equations that are taking into account the time dilation between the ground and the satellite. And if we create a GPS with Newton equation, then your position will be shifted from few kilometers. But if we use Einstein equation, then the GPS is telling you that you're here and you are really here. But so for example, if I was in center of Paris, but if I use Newton equation, then maybe I'm in Gare du Nord or I'm somewhere else, few kilometers away from my real position. So when we use GR equation, GPS works. It just works. And so it's an everyday experimental evidence that GR makes a better job because it takes into consideration the time dilation in gravitational field, for example. All right. Then the before the last experimental evidence is gravitational waves. Gravitational waves. So once again, something that Newton's theory would have never predict. But we know that Einstein theory predict that if two black hole or neutron star or very massive objects collide, then the underlying grid of the universe, the curvature of the universe, will just send a gravitational waves if two very massive objects. Oh, okay, this drawing is terrible, but if two massive objects are orbiting around themselves until they collide, when they will collide, actually they will lose a lot of energy, and this energy is converted in gravitational waves. That this is only GR prediction, and we would never think about it, but actually GR predict them, and we have been able to detect them for the first time in 2015 at LIGO experiments, which is a huge interferometer, very precisely calibrated, and that has detected gravitational waves. This is one more experimental evidence. And the last one we have is the first image of the black hole in 2019. So black hole are purely predicted once again by general relativity. It's a region in space where the energy potential or the mass potential is so dense that even light could not escape it. Means that it really is something that if light wants to escape it, it just cannot. And this is called the black hole region with the Schwarzschild radius being the event horizon. And we have taken, scientists took the first picture in 2019 of black hole. Yes, so that's it. All those experimental evidence, most of them predicted by GR, have been observed, and GR have been very accurate. GR, yeah, the GR calculation was very accurate for those experimental evidence. All right. Thank you for watching.